Horner would like to come up here and introduce to you our awesome guest that's here. Thank you.
Thank you, Crystal, and thank you everybody for coming. It's always good to have one of our physics and astronomy lectures, and in this case, we get to go multidisciplinary because we get to talk about space and bring in geology departments as well. I am happy to have our friend and Oregon Space Grant colleague, Dr. Alex Ruzicka from Portland State and the Portland State Cascadia Meteorite Lab to talk with us. I've known Alex for probably about 5 or 6 years since we started with Space Grant, and I know I've heard about his work at our various meetings, and also he's been instrumental in kind of helping with a little bit of mentorship to help us get our connections with Space Grant off and running. It's always an interesting topic around here. I know I get asked by various people about various rock samples in terms of, could this be a meteorite, could it not? I'm okay on the surface of determining if it really can't be, but in terms of knowing more about the specifics of how to determine basically space rocks of various types and various origins, I will usually defer to someone like Alex that has much more experience with it than I do. And hopefully in this talk, you'll get kind of a sense of what goes on in the meteorite lab and how they make some of the determinations. So without further ado, Dr. Alex.
Thank you. Thank you very much. So hopefully my volume is on. Yes, it is. So it's my pleasure to visit this beautiful campus and new building and talk about meteorites. And I thought this would be a good opportunity to kind of step back a little bit from what I normally do. Mentoring students, doing my own research, teaching my classes, all that kind of stuff, and just step back and look at the lab. So it's going to be kind of a retrospective of the Cascadia Meteorite Lab with a heavy focus on research that we do with students and making discoveries from the first steps at researching these meteorites. So I think that's all I need to say as a prelude here. So I just wanted to talk a little bit about this first slide. And by the way, if you have questions as I'm speaking, I'm okay if you're in the audience and you want to just ask a question. I know sometimes you might have a question and then by the end of the talk, you can't remember what the question was. So I'm good with being interrupted. I'm also good with taking questions at the end too. And hopefully I'm going to have all the support I need for answering the online questions that come into because I'm not actually seeing you that. So let me just say a little bit about this first introduction slide here. So this is a lunar meteorite, and it's one of these things that's a never before studied lunar meteorite. And I have a student who did some initial classification work. And one of the things you might see if you're in the audience, if you can see that there are these pinkish orangey colored clouds, really never before sample piece of the lunar meteorites of the. And so it opens up a whole new research, from like studying a whole meteorite. We often use microscopes here, like optical microscope and scanning electron microscope to examine instances in more detail, and we can use our scanning electron microscope here to generate this false color chemical map. And we assign X-ray intensity to different elements. We can immediately start to see what phases are and textures and what. So we're talking about that. This happens to be one of these meteorites that we thought was a regular, dull, ordinary convex. That's just called ordinary convex. And as it happens to be a undergraduate student who discovered, no, actually, it's one of the rarest types of meteorites that we know about. And it's started like a whole new meteorite group from undergraduate research on this project. And then we do outreach events and, do you have a meteorite that Darren was talking about? So this was taken just last Saturday at the, Southwest Proxim, Northwest Proxim Laboratory. So there, two graduate students and one material lab, looking at people's rocks and yes and no to the Earth. So now I have to figure out how to get this to advance. So it's not advancing for me. Okay, so let's see. Yes, okay, got it now. All right, so the outline of what I'll be talking about is the meter. So I'll say a little bit about the lab. You know, who's in it, what our goals are, what kind of things we do. And then I'll spend some time talking about meteorite classification. This is the path of serendipity. And this is talk about expecting the outside of me. We know we have rocks, but we don't know what they are. We have to research them and make discoveries. And that's meteorite classification. And there are a whole bunch of examples here, and I'm going to give this list of these serendipitous discoveries. I just wanted to point out here, though, that we have different kinds of research going on. So undergraduate student research for these first three examples I'll talk about. Students who are pursuing a bachelor's degree, they contact the lab, get involved. We kind of teach them enough to start going, and then they come up with something about what kind of rock do they have, what's the meteorite, how does it classify, how does it type. And then they sometimes discovers that you just had no idea. We also have things like graduate student research. In this case, we kind of on the rocks that I went to. PhD student is very good at finding interesting things. You know where university kind of things. And that's some research that's been done by people in the lab. So I'll talk about the lab personnel. So we do research on the rocks, and sometimes we're doing a classification and find something uncycled, like uncycled water, where we can expect to see. That's very important implications. Dick's Black Conrad. Dick is one of our founding members of Cascadia in 2020. There's a lot of reasons not to like 2020. He passed away in 2020 in Missouri. But he had this meteorite that he found in a rock shop. He's long time meteorite aficionado, very passionate about meteorites. He recognized this thing looked a little bit different, and so he bought it and he brought it back to the lab and he started making some papers out of it. And then ABS conclusions, these things that are inside other meteorites, and there are ABS rocks that are inside of the meteorite, and that with some serendipity discoveries too. And then I'll end up with just kind of like a reflection of, I think it's right, kind of a reflection of why I think we're successful in doing. Okay, so let's start with a little bit about the lab itself. So this is a curated meteorite collection and associated faculty at Oregon State University of Michelle, established in 2003. Okay, we came up with our logo here, and these are the founding members of the lab. It's me, 2004. You know, I used to be really annoyed about getting carded. Every time I went to the grocery store and when I bought beer, it's like, I don't get it anymore. So I got great. I could probably win my kids for that. You know, they're 17 years old now. But that's what I look like. You know, my wife, who's also the curator of the lab, Linda, there we go. Look like back then, and that's big view. This was a photo taken by the Oregonian. They actually sent a photographer and reporter out to say, wait, we understand there's a media lab at Oregon State. So they did a whole story to make this picture. So that's a long time ago on the Dallas photographer. Ruzicka also joined the lab in about 2018 or so. He's an affiliate, and all of us are faculty. Dick was started off as a science teacher in high school, but his passion was meteorites. He kind of infected his students with the bug, You say, go out there, look for them, see what you have to do, look, find a meteorite, and actually had a student find a bona fide meteorite in Texas. That was very nice. But we all joined forces and we said, time to create a lab. So we kind of started off there.
Dr. Ruzicka.
Yes.
They're having a hard time hearing you online. They were asking if you could stand closer to the podium. I think there's another mic right there. Oh, if not, we can switch out with this.
Well, okay, how does this sound? I thought, oh, great, I have freedom to move. Okay, so I should stand right here. Okay. Okay, okay. So we established the lab with certain goals right from the start. And these are the things that we decided to do right from the beginning. Obviously, we were going to do meteorite research, so we wanted to promote that as much as possible. We also wanted to provide formal education about meteorites and develop classes that we could teach other people about the science of, I would say, planetary science, and meteorites fit into planetary science. We were always interested in doing outreach and informal education too. So a third goal was to increase public awareness about meteorites, lectures and demonstrations, providing a specimen identification service to the public. We are happy, or I should say Melinda is somewhat happy to answer queries from the public. I think that there's at least one or two a day that come in. And I think we're almost unique in the country as still doing that. Other institutions have pretty much given up because it was too much of a pain in the butt. But I will show you a great example of why it's important to still do this, because we had a rock come in from the moon as one of these people that said, I'm not sure what this is. Can you help us out? Help me out. And it turned out to be a bona fide lunar meteorite. That was interesting. Okay, so, okay, you have to do 999 times of saying no, but then you get the one time and it's like, that kind of makes it worthwhile. So we still do it. So if you do have questions about that, we do answer them. We direct people to our website and then we take it from there. Number 4 is a really important one. Maintain and increase the Portland State meteorite collection. And you will see that we've been exceptionally successful at that. I still quite can't believe it. And I think you won't believe it either. We're one of the largest in the country at this point. And this collection serves as a type repository, it's called, for newly classified meteorites. So when you have a meteorite that you make known to the community as a new meteorite, you have to type it, you have to go through a process, I'll talk about that. And then part of that requirement is that you save some sample for future research. So we do that function like other repositories do in the world. Right. Okay, so I think at this point I can probably just use this thing to advance. Yes. Okay, so let me go through these different goals kind of one by one and talk about all the different things that we do kind of in a snapshot here. So we promote meteorite research at all levels. So these photos kind of demonstrate that thing. So upper left here, we have bachelor students, bachelor of science students, as well as community college students, learning about how to do optical microscopy on meteorites and what to look for. They're being guided by PhD student Daniel Shake here, right? So it's good to have students that are at different levels. The more experienced senior students can help mentor the less experienced students. And so I don't have to do it all. I mean, I'm glad to help out, but we have this kind of structure where the students who know what they're doing can help out other students who don't know what they're doing. And that helps a lot. Nina Jamsja down here in the lower left, Bachelor of Science students, working with Dick, cutting a specimen. Dick loved to cut meteorites. Okay, so he said, how many rocks do you have? Someone said, well, I got like 20. I said, great. Let me go there. So that was like his job to cut the meteorites. And I said, okay, he really liked it and he got a lot of satisfaction. I mean, it's fun because the first person cutting open a rock, who knows what you're gonna find. Robert here, BS honors student. So he found out the hard way that to get a BS honors in geology, you had to do a lot of extra work, including a presentation. This is him giving the presentation at the end, but he found some interesting stuff. Daniel Shake here, PhD student that I talked about up here, giving a talk and giving a step out of the second. So I can see this. This is, I can't remember which of these international conferences giving a talk. But you know, making a discovery on one of these features, you know, the lunar meteorite that's potentially very significant. So students doing all sorts of work, and then myself here with Dick and a colleague, a long-term collaborator, John Friedrich, Dr. Friedrich from Fordham University and the American Museum of Natural History, who's done a lot of work with us. So here we are standing in front of actually the poster of Dick's black chondrite that led to a paper. Okay, so the second thing that we want to do at the lab, besides the promote research at all levels, is to provide formal education. And probably the best example of what we've got going on with that is the minor in space and planetary science that we have at Portland State University. So students can take this minor in any kind of major, does not matter. They just have to take these credits, you know, from these categories that are shown on the slide here. And they include a little bit of introductory geology courses, introductory astronomy courses, and then another batch of courses that have different kinds of topics. So right now I'm teaching this Exploring Mars class, which is a pretty heavy duty Exploring Mars course. This is a textbook online put together mostly by Melinda, but with my input. And if you want to know about Mars, you will learn about Mars. We did a major project to research and come up with all the things that we thought were significant. We didn't get this from textbooks. We got this from papers that had been written, and we put together this online course, and it's available to anybody. You know, it's just a fully online class. So the minor is one of the big things that we do in terms of formal education. Public outreach, broadly, you know, taking that as a broad category, including things like talks, displays, specimen identification, informal education, that kind of stuff. So as an example of what we did with that, we had Dick taking a collection of rocks to different places across the state. We did this poster here, and all the red dots were places that he went and he gave a talk, usually in like a library or a Grange Hall, something like that. You know, like sometimes in like a school. He would bring his rock pile and he would give a presentation, and he would be focusing on how do you identify a meteorite. These were really popular events that attracted people of all ages, going from kids to seniors. You know, he took his yellow truck, the yellow pickup truck, and he was very recognizable with that yellow pickup truck. He would drive to all these different places. He didn't quite make it down to here, I noticed, you know, but he got kind of close. So he went all the way around. He went into Washington, Idaho. He loved spread the word about meteorites. He was highly passionate about meteorites. I first met Dick in these science conferences. You know, I would see this guy, and he didn't seem like the standard scientist, right? You know, you could sort of see the type, right? Kind of like me at the time, I guess. You know, like people from universities recognize him, and there was this other guy, and it's like he would always be there. I didn't know what he did, so I talked to him, and he's like, "Oh yeah, I teach." You know, and I'm also interested in meteorites. And later on, you know, he was astounded to discover that that I was moving to Portland, and that I was moving to Portland because my wife was living in Portland, Melinda, and that he had two meteorite nuts all of a sudden in Portland with him. And that's why we said, let's create the lab. We were having dinner at our house, and Dick was saying, it's too bad we don't have a lab. So Melinda said, let's create one. And that was it. So we just said, okay, what's the name? We came up with a logo and all that. And so we just kind of took it from there. So that's the start of the Cascadia Meteorite Lab. But anyway, we got Dick involved in the outreach because he was very good at it. He talked the talk. He knew how to connect to people in rural communities, especially, he was not the standard kind of professor type, liberal, like I might be, he's like rough and gruff and sort of salty and everything. And and kids loved him, and they would just say, oh gosh, this guy's really interesting. And they would make it the headline of the local newspaper, Portland State meteorite scientist visiting. So we got a lot of airplay. It was a great thing. Okay, so enough about that. We created this meteorite display in the Rice Museum that's shown here in this picture. And that was a great thing because the Rice Museum, I don't know if you've ever been up to Portland, but it's pretty much the premier rock museum, I would say, in the Portland area, probably even in the state. They have all sorts of different kinds of things. And we put up our meteorite display right there near the front door. And so they would have students come visit, and tour, and it was a big success. And we created these information panels and loaned them specimens. And after the 10-year loan period was up, they said, great, can we keep the panels, please? Because we want to replace the meteorites that you got. We want to keep this display going. So it's still there, but it's just not our specimens anymore. And then, like I said, just last Saturday, we had Mystery Mineral Day at the Rice Museum. And so 2 of the graduate students in the lab, George and Ben, joined Melinda to do the specimen ID. So we have this long-term collaboration with the Rice Museum that has been very nice for everybody. Okay, maintain and increase the Portland State Meteorite Collection. This is an important one. I want to spend a little bit of time talking about the rock pile. So on the left, I have a graph that shows the growth of the meteorite collection in terms of number of meteorites. So we give a number to each distinct thing, starting with 0, 0, 0, 1. We are now up to we're up to 1,800, excuse me. So 1,800 from one specimen at the beginning, shown right here. So that was a Portland State meteorite that the college had obtained. This Portland State College at the time in 1970. And we've grown since there. So each one of these has got usually multiple samples associated with it, different splits, and we go dash numbers, like it could be 1487-1-2-3, but this is basically showing the general growth. And it's a pretty impressive growth. Okay, so this was a graph that I put together in 2021, and we've grown a little bit more since then. And then some data on the table on the right to show how we stack up to the largest public collections in the United States. So it's ordered by the number of meteorites. So 650 at the top here for the University of New Mexico, Albuquerque. 16,000 for the Smithsonian Institution. It's a big difference. Okay, but look at when these began. So Smithsonian started in 1870. Okay, American Museum of Natural History, the second one here, 1872. 1893 for the Field Museum. All right, and then here we show up in 2003. Okay, so you can look at the number of meteorites and the number that you've gotten per year, and we come out pretty impressively on this list. So as of this 2021, we had 1392 with a growth rate of about 75 meteorites per year, higher than everybody else except the Smithsonian. So why is the Smithsonian getting more than us? Well, first of all, wow, Alex, how do you do it? And we can ask that question, or you can ask that question. But there's an asterisk. This Smithsonian Institution is a repository for meteorites that's recovered from Antarctica. They've had annual expeditions to collect meteorites from the ice since 1976, and all of those go to the Smithsonian. In addition, any meteorite found on any public land in the United States goes to the Smithsonian. So they have that working for them. we will probably never catch up to the Smithsonian. But I'm thinking we're going to be number 2 pretty soon, because we are now at about 1,800 here in 2024. Our growth rate has increased, mainly because we have a PhD student who's very good at working on classification. So we bumped that number up. And so we are now, I'm estimating, in 4th place in the United States in terms of the meteorite collection. This is pretty impressive. Now, there's one other thing that I want to contrast between us and everybody else. Everybody else has gotten large numbers of meteorites donated all at once with large amounts of money donated all at once. We are not that. We started here down at the bottom. We've worked our way up from the bottom, and we have not had large donations of money. We've had some, but not huge millions of dollars donated. So we are the lab that could, the people's collection of meteorites. Started from the beginning at 1 and have worked our way up. We're the grassroots collection. That's another way. It's all grassroots support for our lab. And this is the only model I have of this. We're unique in this way. So I'm bragging about this because it turns out that this is kind of the rocket fuel to help make all these discoveries that we're going to be talking about. Okay, so let's move on. Okay, some pie charts to say what kind of rocks do we have. This would be highly appreciated by people who were like other curators. I'm not going to go into all these different types, but just let me say a few things here. So we are serving as this type repository, as I mentioned. So any new rocks that are recognized get preserved for the future, for future study. As of March 2024 here, we had 1769, oops, I'm doing this upside down, backwards. We had 1769 meteorites and 18 impactites. Those are rocks that are formed as you have something colliding from space. It hits the ground, it creates something like glass, but then like a tektite gets thrown in the atmosphere and then it comes back down. So it's not technically a meteorite, but it's an impactite. But there's only 18 of those. 374 type specimens. So we are the main place to find these 374 rocks. That's one of the ways to think about it. 457 unclassified meteorites, things that we don't know anything about really. That number varies a little bit, but it's usually around 500. And why is this important? Because these are rocks that are never before looked at. They're great things for students to start studying because nobody knows anything about them. So anything that you find out as a student on these unclassified meteorites is potentially something that's useful. And then I just break down kind of like the kinds of meteorites and all that kind of stuff. I'm not going to really talk about the details here unless somebody has a question about it. But I think the pie chart here shows, we have a lot that are recognized that we know about, and then still a lot that we don't know. So they're useful in different ways. The classified ones you can use for building up research projects for, that are like established that you could like maybe get a grant on. And the unclassified meteorites are the ones that would be great for like undergraduate students, for example, to start studying. Okay, so a little bit about the facilities here. Here's our collection room. We have 2 rooms. This one is basically storing the collection. When we're not actively researching a specimen, we keep them in these desiccator cabinets, they're called. And they're called desiccator cabinets because we try to keep the humidity low so that it minimizes the weathering that it's going to experience in the Earth's atmosphere. So we have this room and we have the central set of cabinets that is up on a pedestal here. And we mostly have these samples going from 0001 onwards to what we have, kind of working our way around in this island. You can pull them out, we have them organized so that you could, you can pull them out and sort of find the specimen that you want really fast. We have thin sections in here too, and we have this desiccant that we use to keep the air dry. So remember, we're not supported by some billionaire we have to make ends meet. And so this is the cheap way, the efficient way in terms of monetary expenses to keep the sample safe. We take this desiccant, we bake it in a donated oven, right? Because we're the meteorite lab that could. Not something that we purchased, but was donated to us. We bake it, it gets dry, and then it pulls the moisture from the air, and then it keeps the specimen safe. We have another room, which I will say is everything else. We do optical imaging, we do data analysis, we do sample preparation in this other room. And so we have this setup right here that has this very nice petrographic microscope where we can look at thin section scanner. We have a binoc microscope, we can look at small things. We have a lab bench where we can do cutting and polishing and cleaning and any other kind of sample prep. And then we have a pretty heavy duty computer station to analyze the data that we collect. Some of our data files that we've been collecting recently are easily like 10 gigabytes or so. So we want to have a lot of processing capability to do that. And then we have a scanning electron microscope, a really nice one. This used to be in a different building at PSU, and then it got moved down to about one door down from the second lab room that I just showed you. So it's got a lot of different features on it, and I'll kind of spend a little bit of time talking about it. How does it work? What kind of data can we get? So with this scanning electron microscope, you accelerate electrons very fast using these different magnetic lenses down to the sample. You have an interaction with the sample and different kinds of interaction. One kind is called backscattered electrons. So the electron incoming, the primary electron comes in and sort of interacts with the nucleus of the atoms and then comes back out and it gets you a backscattered electron image. We use that a lot. The main advantage of that is that you can see very, very small things, much smaller than with the optical microscope. You can also have a primary electron, and that is measured by this backscattered electron detector, which is right here. You can also have X-rays coming off of the sample. So what happens here is the primary electrons come in and they interact with the electrons around the nucleus, bumping them out of the shells that they're in. And then you have another electron that falls into place. And as it does that, it releases a characteristic X-ray. What is a characteristic X-ray? It depends on the element, because these electron configurations are all based on what's going on with the nucleus, the element. And so we can analyze the composition of materials with this energy dispersive X-ray spectrometry system, the EDS, this thing. We can get chemical maps. We can also get spot analysis, and I'll show you some examples. This is the EDS detector right here that does the chemistry. Okay, so the other thing that we have is this electron backscatter diffraction detector right here. This is a piece of equipment that not too many other people have, and it's the bulk of my research at this point. It's a very nice thing. What you do, so these other systems right here, you have a sample that's at like 0 degree tilt, it's flat. But with the electron backscatter detector, you have to actually tilt the specimen 70 degrees to the horizontal. And what happens then when the electrons come down is they have a diffraction condition. They actually get diffracted into this pattern that you see right here. And this tells you something about the crystal structure that you have. So you can analyze the kind of minerals that you have and also their orientations. So that's a very useful thing. I'm using it a lot right now for analyzing deformation type processes. Okay, so enough about the lab. Let's talk about how do we get to the serendipity and how do we get there via meteorite classification. So the basic idea is that we study new meteorites, we get initial data for them so that we can get this classification done. I'll say a little bit more about that. Keep your eyes open so that you look for interesting or unusual things that don't fit. But basically you have a rock from the rock pile, you have the researchers, you have the research tools, and you can make discoveries. That's the basic idea behind this. So in terms of classification work, it's new meteorites, things that have never been looked at before. Okay, so that makes it a little bit different. The researchers can be either one of the people in the personnel for the lab, it can be visiting scholars we've had, they can be students. The research tools, the optical microscopes, the scanning electron microscope are ideal for this kind of meteorite study, this initial classification work. And then we do have this new EDST tool that we can play with too. Okay, so classification, what does that actually mean? It's the initial typing of a meteorite. So you don't know what you got, you have to say something about it. Does it pigeonhole into something? You have to submit, you have to collect the appropriate data, then you have to submit it to this international committee for approval. It's not something that you can just do. You have to actually go through this process. You get an official name for the meteorite, and names of meteorites are all based on geography. Where were they found? A lot of them that I'm going to be talking about are NWA for Northwest Africa. They were found in the Sahara, sold in Morocco to some dealer, and then they ultimately wind their way to us. Okay, so then once you get the official name for the meteorite, your meteorite's approved by this committee, then data is entered into this international database and the repository sample is established. So here's an example of what that database looks like. And you can see that they talk about the name, the abbreviation, how much mass is available, where was it found, what kind of type is it, and when it was approved. Okay, and then to show you that it's not necessarily that easy to get this information, I have this. And this is what you are never supposed to do, right? You're never supposed to show a slide with bazillions of tiny little things on it. So the point here is not so that you can read it all, but that you can see this is all stuff that we have to determine and figure out and then send to this committee. This committee is the nomenclature committee of the Meteorological Society. And so you send this information off and they evaluate whether they believe what you did is correct and whether you've done everything correct and you've typed it correctly and the name is okay. And then they say, all right, we'll approve it. And then it becomes an official meteorite. And then you can say, hey, I've got another meteorite. So this is all the stuff that you have to do. Okay. So kind of in picture form now, this is how you classify a meteorite. It's a multi-step process. First thing is you have to take your rock sample and you have to make a thin slice. Because pretty much you have to have, I think it's almost always required that you have a thin section. You can maybe do it without a thin section, but it becomes harder. The kind of information they want almost requires a thin section. So you cut off a piece and you prepare a polished thin section. Okay, so oftentimes you put it embedded in epoxy, and you can polish up the one side, you can cut a thin slice that's parallel, and then you can adhere it to a glass slide. Yes?
What is the smallest sample you could put into one of these thin sections? If you're really
yeah, so
in there for some punishment.
yeah, so you can do it. So like the epoxy right here, if you could put your samples, even if they're tiny little things, and you can kind of push them all down so that they're at the same level, they can be quite small because you just have to, it's kind of like, can you overlap the width of the small samples? If you just have one small thing, you could just do it for one, but then you'd have one little tiny thing inside this big plug. It's a little inefficient, right?
We're thinking of a field of many small.
Yeah, that's what I was thinking you were thinking. So like micrometeorite type things. So you put your micrometeorites that you want to maybe size them so that they're all about the same size. You pop them into one of these plugs, you encase them in epoxy, and then you can make a thin section. You get different ones all at once. So there really isn't any small size. It's kind of like, can you manipulate it and put it into the plug properly? And so long as you can do that, you could make a small section. Yeah. So you make your thin section. And by the way, we send them out because it's like too much time to make your own thin section. I mean, it's work. So we send it out, we pay somebody to do it, and then they come back with a thin section. Sometimes we say, this is a great section because it was prepared nicely. And sometimes we say, this is not a great section, right? So we have our opinions on that, but we then start looking at them with our microscope system here. And we can look at them in terms of plain polarized light. So light's coming through, it's polarized once, so it kind of cuts the glare. Or if you have a second polarizing lens, you get what's called cross-polarized light right here. That shows you the mineralogy a little bit better. See things colored. And then you can also just have light reflect off the top surface, and that's reflected light. Each one of these things gives you different information. So what we typically do with students, say an undergraduate student, we say, hey, we're going to give you this rock. We sometimes let them pick. We'll say, you got a choice of these guys here. Which ones do you want to do? And they say, okay, I'll pick this one or this one. And we say, okay, now your task is to use the microscope to image these things in all three light modes. And the pictures have to be good quality. We need to be able to see all the different minerals. We can't have things overexposed, underexposed, too contrasty, not enough contrast. So we have to be trained a little bit how to use the microscope, and then they get these mosaics built. And then we say, great, thank you. Now we have to figure out what it is that we're looking at. And so we go through the process, but it starts here with the thin section and the optical microscopy. Then we use our scanning electron microscope to obtain chemical data for individual minerals. We get points, like in this picture, this is a backscattered electron image, and I did the wrong thing again. Right here, and you can see we just analyze in certain spots here. You can move the cursor where you want to get an analysis. You can get a false color map. I don't have the key. Well, I do have a key, but can you read that? Not really. Doesn't matter. The different colors represent different minerals when we can figure out what they are pretty quick because we have experience. Okay. Then you have to process the data. You get all this data, and it's like, well, how do you deal with it? So we have to teach them how to do that kind of work. Then you say, well, okay, now what does it mean? And let's get all the information we need and submit the information to the nomenclature committee of the Meteorite Society for approval. And hopefully it gets approved. So those are all the steps that you got to do. So it's kind of like a mini research project for each one of these things. Okay, so that's all of the background leading up to the serendipity stuff. And so I want to go through these different examples to show you kind of what is interesting and how it works. So this is sample CML005. And the -2 that's the particular thin section that was used by Carla Farley here to do her classification. So she was a BS honor student at the time. So we said, you know, we got some of these low numbers that we've never actually looked at. Let's give some of those to Carla. They're going to be certainly these very common ordinary chondrites. Official classifications, ordinary chondrite. And so they're going to be pretty easy and straightforward and not very interesting, right? Well, no, this one was actually different. So Northwest Africa, NWA 8614, the least heated Winonite. This was already a rare type. Winonites are very rare. They're metamorphic rocks that have really been cooked, probably by, you know, radioactive decay in these asteroidal bodies, really cooked and heated, but they're not that common. So, you know, we had Carla work with graduate student of mine, Catherine Armstrong. You got this data here, this map, false color map, chemistry map of this thin section. And we said, well, this is a strange Winonite because it has these things that are circled right here. What are these things that are circled? These are chondrules that you never see in Winonites. Chondrules are things that form in chondrites. They're little melted blobs, and they form in space in the protostellar disk phase of the solar system, where before there was even planets, we had gas and dust, and for some unknown mechanism, melted some of that dust and made these chondrules. So we see vestigial chondrules in this metamorphic rock, and so it was like, this is a strange Winonite. It looks like it could be the precursor to the standard Winonite, one that wasn't heated as much. So we said the least heated. Well, fast forward to 2023, and these different researchers said, you know what? We have this new group of meteorites. They're kind of like Winonites, but they're a little bit different, right? And so they proposed this new group. And the table that I show you here has Farla et al. 2015 mentioned, and we were one of the first to start recognizing there's this new kind of meteorite, the sample 5. Okay, so we right away, we found something really interesting and rare and significant. So these people did one meteorite. You'll notice this study was this NWA 090, and they relied on the literature, including our abstract and poster, to say, hey, we got a new meteorite group here. So that's actually pretty significant. Serendipity number 2, the unusual NWA 4859. So here's Nina working with Dick. And Nina was an undergraduate student, and she has a peer-reviewed pub. This work that she did as a classification, there were strange things in this rock, and it led to this peer-reviewed pub. And I'm not going to talk about all the strange features. There were various things that were interesting, including these big igneous regions. You can sort of see this darker gray here is different than that. So this is one of these big igneous inclusions. Comes in later, I'll talk about. But one of the things that I did want to mention here is that Nina and I developed this shock stage scheme. So this is a way to use optical microscope observations to say something about the shock history of these rocks. How intensely were they shocked? You have lots of collisions in space, especially early on in the solar system history. Lots of things were colliding. And you can use your optical microscope to say something about how much shock did you have. So we developed this new classification method, and it's now being widely used by our group. And this is an example, in fact, of a chart from a paper that is now in peer review that I put together using the shock scheme that we came up in 2010 with an undergraduate student. Very nice. Serendipity example number 3, Ryan Brown, bachelor student. He took the lead on this. He found this shock vein in this meteorites, Buck Mountains 005. And it's a pretty impressive feature. And so we did a lot of work. We teamed up with other researchers here to do things like tomography work. So we analyzed a bulk piece of this rock, and we said, you know what, this shock dike is a sheet structure that goes all the way through the rock, and it doesn't hardly have any of the metal or the sulfide that you would typically see in the rock. It's been moved out. So it's like, okay, there's something about the shock process that moved those other things out of there. And we thought that's an interesting result. And so did other people. So we had all these abstracts. We started off with Melinda, and then Ryan, and then Ryan. And Ryan went down to, AGU to present this paper. And he caught the eye of an editor for American Mineralogists who said, gee, I'd really like you to contribute this to our special issue that we're going to have in American Mineralogy on building cores, because your work is actually relevant. You're showing a process that takes impacts, and you're able to move the metal and sulfide around with that. And so here's this paper that was published, peer-reviewed paper about this topic. American Mineralogist, pretty prestigious journal. Now this meteorite, as well as other shock veined meteorites, are the subject of further study by a current master's student, Vince Ruzicka, or I guess it's Ruzicka. Serendipity number 4, new kinds of lunar rocks. So Seattle chocolate has moon rocks. They're milk chocolate, truffle bar with popping candy. They're really good. But these aren't the moon rocks I'm going to talk about. I'm going to be talking about lunar meteorites, the rocks that have been blasted off the moon because of another impact. They provide free samples from all over the moon, unlike the Apollo and unmanned missions that have gone to very restricted locations in the moon to collect stuff. These meteorites can come from anywhere on the moon, and so they provide a more representative sample of what's on the moon. And here's Daniel Shape, who's been taking the lead on these things. So this is a reverse chronology, starting with a pre-Daniel abstract here. This one, this was the meteorite, by the way, that came in from somebody that said, could you help me identify this? I don't know what it is. It's not like the other meteorites that I know about. And it turns out it wasn't like the other meteorites that the guy knew about. It turned out to be a new type of lunar meteorite. This is our first classification of a lunar meteorite in the lab, and it was a special one. And then Daniel just kept finding more things after he came in, all the way up to this year. So here's that rock that was brought in. So it's a little different. And here's another lunar meteorite, and you see this one thing down here looks a little strange, this green. It's green because it's all this one mineral, olivine. Based on the composition of this olivine, we thought, this looks like something that could have come from the lunar interior. It could be a piece of the lunar mantle, which we never collected with Apollo. And so this is a false color chemical map. And this is what it can look like with this electron backscatter detector, where you get crystal orientations. It turns out it's a great technique to use on this, because here you see nothing but just a pile of olivine. But now in this, you see texture. And what we can say is this blue stuff is one big olivine that was broken off and broken into all these little tiny pieces that end up having these different orientations. The colors represent the crystal orientations. So we're learning about how this sample was actually impact reworked. Down here, we have these Beshar 009 granitic type clasts. These are calcite clasts. So they have things like potassium feldspar and a silica phase. We determined what that silica phase was. I think it was quartz mostly. Possibly related to these high iron things, because we sometimes see some of the same minerals. So this is a whole new subject area too. There's been some work done on that, but this is, how do you make evolved chemical rocks in the moon when you don't have plate tectonics like you have on Earth? And then the sample, which I already mentioned from the introduction about this pink spinel. One of the interesting things is that it's been found from orbiting missions based on reflected light. People are able to look at reflected light spectroscopy and say, we must have this rock type on the moon that we never sampled with Apollo. It must have this characteristic of this and this. And Daniel was the first one to find it, actually in a rock. It's hugely important because it's linking the remote observations from orbiters, from an Indian orbiter, to an actual rock that we can study in the lab. Serendipity example number 5, unexpected water. So here's Melinda, curator of the lab. She took the lead on this and has written 2 abstracts on this. So the first one was this guy on, we found a strange class that was full of these phases that formed under very wet conditions in an otherwise dry chondrite meteorite. How does that work? We started expanding to other people. There's John Friedrich and some other people coming in, Mark Fries, to study this thing. And so we have another, and this needs to be written up in a peer review club. It's a really interesting thing. Let me show you a picture of what it looks like. So a backscatter electron mosaic is right here. That's the outline of the class. It looks a little different than the surrounding meteorite. All these things are chondrules in here, but the in-between stuff between the chondrules is different. You can see that in this picture, it's brighter. If you do one of these false color maps of the edge here, this broken edge, this is what the regular meteorite host looks like. And this is what the altered class looks like. It's full of clay minerals, things like smectite, serpentine, hydroxide phases, other things. It was formed under highly wet conditions, and it's sitting here in this dry rock. We did some Raman spectroscopy with Mark Fries here, and this is a map of macromolecular carbon as these colors, which is like tar-like substance. And it's enriched in the class. So somehow when this thing formed, it got water and this organic material, this macromolecular carbon. Could have been like a comet maybe that hit and delivered these things and then set up this process of reacting to make these new phases. Serendipity number 6, Dick's black chondrite. So here we are in front of the poster, 2015. Here's the paper that finally got published in 2020, and I want to read the little asterisk thing here. This paper is dedicated to the memory of Richard Dick Pugh, who passed away during peer review, 2020. The NWA 8709 stone was found and purchased by Dick in a local rock shop in Portland, Oregon, and shortly thereafter recognized as unusual and significant. So he didn't quite make it to see this thing get published, but he was very close. It's an interesting rock. The bottom line is it's really rare. It's what's called a melt breccia, so that you have these chondrules and constituents that you would normally see, but in between it got melted. So it makes what's called a melt matrix. And so in this table, you could say, well, number of recognized ordinary chondrite melt breccias are very rare. So this one type where you have very little metamorphism, type 3, it's only 0.1% of all recognized ordinary chondrites. Extremely rare. And even when you take all the other kinds, it's very rare type, and you're found by Dick in a rock shop. Only because he had enough experience to say, this looks a little different. And so he brought it in, and it's like, wow, it really is different. And so we have this story of this thing was porous, it had this collision, and because it was porous, it was allowing it to melt in between the other constituents to make this melt matrix. And then lastly, serendipity example number 7, igneous inclusions. Now, way back in my postdoc days, I studied these things. And then Nina found some more of these things. And then we had this rock that needed to be classified from Saskatchewan. It was a new fall. Now, what's a fall? A fall is a meteorite that's observed to come down, and then somebody goes picks it up. That's not that common to have a fall, because it's hard to actually find these meteorites after you see them come down. It's more likely you're just going to stumble onto them or find them. Say you see a rock in Antarctica, you pick it up. You find a rock in Sahara, you pick it up. You're more likely to get what's called a find than a fall. But anyway, here was this new fall in Saskatchewan. And Alan Hildebrand, professor up at Calgary, we're good friends. We were fellow graduate students at the University of Arizona. He called me up and he said, Alex and Melinda, you guys do classification. Could you help me classify this new rock that I found? It got named Buzzard Coulee. We said, okay, sure. So Alan flew down. I didn't get the whole story. He was in a big rush. So he wanted to get this thing out as an abstract for the upcoming Lunar and Planetary Science Conference, which we did. And it was classified as Buzzard Coulee. But what I noticed and what Melinda noticed is that it had these light colored rocks in here, these inclusions, and they were very interesting. And it looked like they were telling us a story about how, something important about how these things formed. So I said, you know what? We got these inclusions here in this new meteorite. We had the inclusions from Nina. We had the inclusions from my postdoc days. This is actually really interesting. It could be good for a grant proposal to NASA. So we published this paper, right? And I was successful at getting this NASA grant to study these things. So this is an example of how a classification project, this rock that needed to be classified for Alan, turned into this NASA-supported research project. It wouldn't have happened if we hadn't had this fall into our lap. So that's a great example of serendipity. And published a paper here in 2019, joined forces with some other people, including, did that again, Catherine Armstrong, Christy Shepard, graduate students, as well as a couple of colleagues from England here. And we studied a large number of these inclusions, and we said, okay, we have two major origins for these things. Some of these things form as what we call planetary impact melts. So things hitting asteroidal bodies, making melt objects. Or the second class was, these are things that formed on the protoplanetary disk by some unknown heating mechanism. They were evaporating and they were getting changed compositionally. And so there was a second nebular melt hypothesis. So we have these two different things. So all coming from classification work. Okay, so that's the serendipity discoveries I wanted to talk about. Now let me just kind of reflect on things in general, the lab and how we've gone. Well, we're actually doing pretty good. We're on the world stage, I would say, as exemplified by what happened in 2022, when we had these 3 falls from around the world that became classified by our lab, and we got type specimens for it. That doesn't happen. Not even the Smithsonian does that. I mean, we don't have that many falls in general, and one lab doesn't get them all, right, in 1 year, but we did. So let me go through the sequence here. What happened in Mississippi, we had this fall of the Cranfield chondrite. This is classified by the crew at CML, Melinda, Alex, and Daniel. Type specimen is half at CML and half at this other organization at Space. So that was April. Then in May, in the Philippines, around the other side of the world, we had an H3 to 5 chondrite called Pongo. And this was classified by Melinda and Daniel, type specimens in our lab. Then in August, we had the H5 chondrite fall on Great Salt Lake, actually on the lake bed. First case was found by Sonny Clary, classified by Jim Carter, Melinda, and Daniel, type specimens at the CML. So this is pretty amazing to have all of these falls come into our lab. But the nice thing about it is that we are known now for being a repository. People are sending us samples, even if they are doing the ones classifying it, because they know that we're going to take care of it, and we're an official repository and we know how to do this stuff. So it's leading to collaboration with all sorts of other people. So we've been pretty successful, I would say. We have the rock pile. We have researchers. We have research tools. We have institutional space. The university has given us space, right? But it turns out we've been too successful. We're gonna need more space. We are getting to be one of the largest repositories in the country. We can't fit indefinitely in the room that we have. We're gonna need more space. Plus, we need the money. So if anybody out there in the audience or listening is one of the deep-pocketed variety of people who have a lot of money, think what you could do by helping us out. We have done more than other people with very limited resources. How much more could we do if we had all those financial resources? So the money is sort of an issue. We do need to pay for things like equipment use. It costs money to run the SEM, costs money to make thin sections. We have consumables that we use up. So we could always use more money. So we have a lot of the things that we can control, but we don't have unlimited pockets. I know that some of the other institutions, other repositories, they have large acquisition budgets, tens of thousands of dollars per year to collect, to buy meteorites, to put in their collection. We don't have that. But we're still beating them out in terms of acquiring specimens. And you could ask yourself, how do you do it? And that's a good question to ask. How do we do it? Because we don't have the funds, but we got a lot of other things, including this: vision and hard work. We had the vision to create the lab and to go the way we want, not because we were told, it's because we said we want to do this. And then the hard work, that's probably one of the main things. People say, how do you build up your collection? Well, we work. And they say, yeah, okay, right. But it's true, because we all have to put in a bit of our time to make this enterprise work, right? We do it, we don't get paid to do it. We do it because we want to do it. So the goal that Melinda and I have for the lab is to leave a legacy. We need to have a paid curator position, proper paid position, not shoestring budget, because there's going to be a lot of work that needs to be done to maintain this collection in the future and to keep it growing. But it's the hard work. You know, you do it because you love it. You do it because it needs to be done. And then you say, hey, I'm available. We'll take good care of your specimens. You need a tax write-off for donating to a public organization. We can give you that. We can make trades with you. We can make you happy. Ultimately, we're all about growing the collection, right? And doing something with it. So that's kind of the success of the CML. So before I take questions then, I just wanted to show you the people who are now with us in the lab, starting with the Graduate students, oops, first the wrong one. George, Vince, Daniel, and Ben. So we have Rick Hugo, electron microscopist, that's his specialty. Melinda and myself, looking, I guess, kind of happy because we're collecting data. And then we have 3 undergraduate students here, Dipper, Ash, and Jennifer, all working in the Oregon Space Grant project that we've got going on right now to classify, and they've been very enthusiastic, much more motivated than previous students. They have said, give me what you got. We'll take more, we'll do it. So that's what we love because they're helping us out and they're helping themselves out, right? So this is our happy crew. So that's all I got for you. Any questions? Yes.
Do you have any tektites?
Yes, we do.
Have you imaged them in thin section with the petrographic microscope or the microscope?
We have the tektites, but we have not done anything with them. There hasn't been a need for us to do anything with them in the thin section. If there is a need, because you've got a need and you can make a good case that we should be looking at them, we could do that. But they're nice specimens as a bulk piece because they have, flow textures and aerodynamic shapes, and they look nice. And we haven't had any need to do any cutting into those things.
Well, in that case, using your imagination, if you cut one out, you think there would be a textural difference between the outside and the inside? Maybe reflecting its quenching during its path through the air. I'm curious because I had an old project from many years ago, and if I knew the thermodynamic pathway that tektite traveled, I'd be able to implement a numerical model to finish that. But since I don't know that, we can't. And I thought looking at texture might be a way to see how that's it.
It's a great question. Would I expect that there would be something interesting inside the tektite? Hard to tell. Because
Just be all glass.
it might be all just glass. I mean, clearly you can sometimes see some structure on the surface where the melt has actually been aerodynamically shaped. I would think that would make it different in the interior. That's not seeing that, but I don't know for sure. It's a good question.
You talk about magnet traps or actually, of course, magnetic meteorites. But that's only a small percentage of the meteorites fall. Right? So the magnets are only catching the ones that are magnetic.
Yeah.
And what do they look like?
So we don't catch the meteorites. I mean, maybe Crystal and Aaron catch the meteorites with starfall.
The micrometeorite.
Yeah.
It's kind of a starfall project where we put some at the bottom of the storm drains. Yeah.
So but I agree with part of your question where you said like there are sometimes magnetic or sometimes not. That is true for all extraterrestrial stuff, it turns out. And it's the one thing that people are most often going to contact us and say, I've got a rock and it's magnetic. I'm saying, congratulations. It could be a meteorite. It might not be a meteorite. It tells me nothing because there's a lot of terrestrial stuff that's magnetic. So then it's a question of like, what kind of magnet are you using can make a difference? Like how strong is it? So if you have a super sensitive magnet, you'll pick up everything. And because it's magnetic, that says nothing. Might actually be better if it's not a very good magnet, because then you will only pick up things that are like metal. But then there's a lot of metal that's artificial, right? Slag and other types of things. So it's the least reliable property of extraterrestrial origins, magnetic property. And that's the one that people most often come up with. Much more reliable is how does it look? What's the shape of the specimen? Can you see a fusion crust on it? Black glassy coating. What does it look like if you break off and you see something in the interior? All of those things are much more important than diagnostic. So how does that help you with micrometeorites? I don't really know.
Yes, I don't.
Well, I have several magnets, and I was thinking about putting them into the screen.
Yeah,
rainwater one. Just
Yeah.
out of curiosity,
yeah,
to see what.
Yeah. do an experiment.
This is a little similar to kids' inquiry. There's a place in the southern Oregon coast where you are going down the hill around the mountain. And the stream on the other side of the road is going up. The stream is going up. And I've heard, and I'm wondering if you know the story of the Port Orford meteorite.
Corridor for meteorite? Oh, Port Orford.
It's a big meteorite from generations ago that has historical importance because of the, there was a fraud involving it.
Yes. Yes, we know about that. So if you go to our web page, we say here are the recognized Oregon meteorites. There's 6 of them. And then here are some purported things that are not meteorites, including the Port Orford. Now, I'm not necessarily an expert on Port Orford. I read what other people have written about it. You know, you have to be careful because sometimes people actually are very keen on coming up with a discovery. And they do things that are maybe a little bit unethical, like transportation has happened. We've documented some cases. I don't know if it's true for Port Orford, but there are some cases where things have been moved from one spot to the other and then claimed to be a new meteorite. We have gotten very good, I think, at identifying what we are suspicious about. And Port Orford is not really like, we don't consider that to be a real meteorite. We've had people claim, as an example, that this meteorite with this pinkish dust on it was found in Oregon. I can tell you where it was found. It was not found in Oregon. It was found in the Sahara Desert, which has that pinkish dust. It's a very characteristic pinkish dust. I've seen enough specimens. I can ID that. I can tell you it comes from the Sahara because of the dust. So, you know, it's like, thank you very much, you know, but no, we're not going to pursue this anymore. So, you know, we try to be nice to people, but we are also like highly skeptical. That's kind of like, I have to be convinced. So when we got this quote unquote new lunar meteorite, it's like, let's go over this again. Is this really true that we got a brand new lunar meteorite of a new type from some guy that just contacted the lab out of the blue and said, can you help me out? And you know, it checked out. He bought a bunch of rocks at the Tucson Gem Show. Most of them looked one way, they were chondrites, and one he thought was a mistake. It wasn't a meteorite. Well, it turned out to be a meteorite from
So I usually ask this question, in general of our students, but you mentioned a lot of cases in the presentation about undergraduate students that you've had doing work. If you had to give advice to undergraduate students that want to get into planetary sciences or analyzing meteorites, what kind of advice would you give them?
Work hard and just try to learn whatever you can, whenever you can, you know, whatever and whenever you can. Take advantage of the resources that you've got at wherever you're coming from. And if you're willing to open your mind and you're willing to like put in the time, you can do a lot. So I can tell you, for example, Nina, the undergraduate who was first author on that paper, killed herself to get that paper out. She was in the lab day after day after day after day. And by the way, there were 5 bazillion revisions of that paper, which I spent time on too. So that was way long to get a paper out. From my point of view, it would have been much faster for me to write it, but it's like, Nina, you take the lead on this. But she was so motivated, and she won an award from the university for getting that paper published. She got an award from the College of Liberal Arts and Sciences for this work. And it was great. I would have loved to have her later as a graduate student, but she shone very brightly, but she just was highly motivated to do what you need to, and she was a very good student. She took her studies seriously, and she just put in the hours and time.
I have some questions online. I also want to ask if you didn't get a chance to sign in, we have a sheet up front here. We just ask for your name and email. It's just a way that we can kind of track, people participating in these types of events and being able to provide these more of these types of lectures. So Nicole Kennedy online had said, were any new or recent discoveries exceptionally shocking or exciting?
Well, what weren't? I think that maybe what comes to the top of my mind is some of these new rock types that Danielle's been finding in the lunar meteorites. They are stunning. They are totally stunning because they are what was predicted and then some, right? So, and when we thought it couldn't get any better, he comes up with another one. And it's like, wow, this guy is good. So Daniel loves to classify. So he'll probably be watching this, and so he can hear me say that. I really appreciate that about him. I have to sometimes say, Daniel, you also have a PhD. So time to step out and do the other work that you got to do for your degree. But it's really helped because he takes these rocks and he classifies them, and he often finds interesting things because he's the first one to see something. So I would say that's pretty amazing.
Thank you. We also have Val, who is down, they're actually hosting a watch party at our Curry campus right now. And Val asked, what is the process for the public bringing in specimens for identification? And she said, her apologies, you've already said, she was just desired.
Yeah. So what we do is we discourage people from driving to Portland and then coming in. First of all, the building is locked. So, like if you're a student or a faculty, you can get in, but otherwise you can't get in. And we've had some people say they've spent all this time driving and they can't get in. And we don't want people to do that. What we want people to do is go to our website, meteorites.pdx.edu. It's very simple. And there's a page there's a link that, one of these radio buttons that says what to do if you think you got a meteorite. If you click on that, it takes you through the steps of what you should do. And what that generally involves is you send an email to Melinda as the curator, and you send, not 5 bazillion pictures, but like a good quality picture, plus a little bit about, circumstances or whatever. And that is enough to get us going. And so we kind of use that as a filter. And then if we want to work on it, we will work on it, but we feel like we're under no obligation to just say, okay, we're going to study your sample. First of all, we can't possibly study all the samples that people want us to, right? I mean, we would really need that deep-pocketed, benefactor, because you'd have to hire a big staff to do all this work. It would be overwhelming. Like I say, we get several to dozens of emails every week, or phone calls. People phone call, even though we say don't call, they phone call. Go to the email, and that's a lot. It's a lot to keep up with. And sometimes we say, you know what, we'll work with you. But other times we say, we just don't think so. Sorry.
I don't know how many we will actually, when we get people stop here with things that we'll want to ask the professors.
Yeah.
To help them out. So
Yeah.
there.
Yeah. It's a lot.
I don't see any other questions online. Are there any questions here?
I just had a quick, I was wondering how you grow your collection. Is it because people send you samples and then you get to keep these, or?
Yeah. Let's go back to the charts.
Do you want to see the same question again? So
It is
online. I was curious as to how you grow the collection. If people are sending you samples, do you get to keep them, or a slice of them, or I'm just curious.
Yeah. So we make all sorts of arrangements. So it is a good question. Because we are doing something that other people aren't doing. You know, if you just look at this data. Why are we so successful? So we make ourselves available to, if you want a meteorite classified, for example. Okay. Do you want to make a donation to the lab to help pay for the expenses? Do you want to submit additional, so for the people that are like collectors, or I should say dealers, let's call them dealers, they actually are trading in meteorites. They have a tremendous need to have the rocks classified. Because if it's just a rock, it's a rock. If it's an official meteorite, now it's money potentially, right? So they really want it classified, but there's only a limited number of people that can do the classification. We can do it, but what are you going to do for us? So do you have something spectacular that we haven't seen before that we'll just, it's so important for our research that we'll just do the work? We might do that. Do you want to make a trade? Like, can you give us additional samples if we work on this one? We can grow the collection that way. We sometimes say that. We always say like, okay, you know, we've done some work for you, but it's kind of, we need like to cover our expenses. Would you consider a donation, not a, you know, for, you know, pay for work? We don't do that, but we just say, we have this, you know, way that you can donate funds to the lab online. It's really easy. Want to just make a donation? That'll help us out. You know, so we have all sorts of different things that we can offer people. We've done the tax write-off thing too. Do you want to donate your specimen and get a tax write-off? Just give it to us. You get a tax write-off. You don't necessarily need to store your rock. You don't need that, right? But maybe you need the tax write-off. We can do that for you. So we have a lot of different ways to help build this. That's what I mean by the hard work. We're making these trades, deals, you know, and stuff like that. And the goal is we want to get a diverse collection. We want to get a larger collection. We have to make it work with the resources that we have.
I actually have a question myself. Have you found many of the grant opportunities focused in the work that you guys do?
They're not as common. It's very hard to get these big NASA grants. Let me just say that. It's highly competitive. There have been some cases where, like the one example, the Serendipity number 7, I think it was, where it has actually happened from this kind of classification work. More often, though, we use the collection as supporting the need for this kind of study. Like, let's say that we have a project that is defined, but we need to have samples to work on. If we can say that we have these samples in-house, that helps the proposal go through a little bit easier, right? Other than, oh, we have to requisition samples from NASA that could take months, you know, whereas if we have the rocks right here in our lab, we don't have to do that. So that's a plus. But we've done that more often than, oh, we have like a discovery that then snowballs into a grant. That's not so common.
I guess one other question from that is, have you had support from your, or much support from your local communities at city or state, county, state level on, because I know like this community is amazing. We have a lot of help with different areas, whether it's business, the foundation, the tribes, and they kind of all pull together to help us, you know, and all of us in the community. And so I just was curious up there in the Portland area, do they do that?
No. They don't know. People are shocked to find out that we have this big meteorite collection. They've never heard about it. It's funny because you go to a rural community, you know, like Dick did, and it's like, wow, it's like the main event. It's like written up and it's like, wow, press coverage. It's all lost in Portland. You don't know. You don't get that. In fact, you know, I prepared some of these graphics for my dean to say, you know, we kind of need a curator position. We might need some more space coming up. And he said, you're doing great work, Alex. I had no idea. But he's providing space. And, you know, I had a tenured position. That's great. I mean, that counts for a lot, right? So I have gotten institutional support. I once asked for a support letter from the mayor of Portland for getting some equipment. I got it. But do I get Other kinds of support from the community? No, I don't think so. Yeah.
I have a question.
Hold on one second, the online.
Are you lending library your collection to other researchers somewhere else?
Yes,
On the same.
yes.
And the second question is larger is, you talk about extraterrestrial, has there ever been a discovery of extrasolar? Or suspected extrasolar?
So yes, the answer is yes, if I can like make some conditions on it.
Okay.
So, what we have is in some of these chondrites, these common types of meteorites, you have what are called pre-solar grains. They are grains that formed in some other solar system, usually associated with a dying star, sent like a supernova or red giant, sent its debris into space. You form some grains in space. Those grains work their way into a molecular cloud, which then collapse to form our solar system. So those little bits of these pre-solar grains are extrasolar. They've been identified as such because they have isotopic compositions that don't match normal solar system matter. They formed, and in fact, you know, I know you guys are interested in like astronomy and astrophysics and stuff. Astrophysicists are using these grains to study stellar processes because they are actually samples of stars. So they have like particular isotopic compositions, for example, that represent a particular shell burning zone in a star, for example. And so it's direct samples of star material. So that's pre-solar. And then we have had I think 2 asteroids now that look like they were on hyperbolic orbits that came through our solar system. So they came from someplace else. So it used to be thought that was impossible, but now it's like, no, it happens. So something like that does come into our solar system. Do we have rocks of those things? No. But we do have stuff that's floating between different star systems like that.
There's a speculation that our 2-hour planets might have been capsules.
Yeah.
And plus other things.
Yeah.
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 Thank you.
Mm-hmm.
The shock depth. Why do the sulfides need it? They get squeezed out under pressure? What's going on?
That's a great question. We think that they formed by a shearing process, that those legs formed by shearing. So maybe if you bring up the temperature high and you're melting and you're also doing shearing, that you can take that material out. It is presumably a different viscosity, you know, than the silicate stuff, so maybe it comes out. I suspect also that that's not the only change, but we don't really know. Current student Vince is going to be telling us, is there any other changes chemically in the silicate part? Not just the sulfide in the metal, but in the silicate part. I think the answer is going to be yes, but we don't know yet. But why does it happen? That's a great question. I'm not sure.
Does anybody else have any other questions? Or I guess we'll give around for humans afterwards, so if you guys want to go up and talk to them, and again, if you would just sign in up front, that would be really helpful.
Thank you very much.
Thank you all again for coming.
What's the next program?
May,
Is the next one my paleo?
yeah, May 23rd. What's the,
May 22nd, I think.
May 22nd.
The Tuesday, let me look at my calendar.
and I was like, I gotta look at my calendar just so that
First, good thing I looked.
21st.
21st at 6 p.m. will